Welcome back to the channel. Today's episode 23. I was actually recording this last week, but life got in the way, so I had to stop the video, and it wasn't a good session anyways, so here we are, Unit 10. We've worked on confidence intervals, we've looked at confidence intervals for proportions, and then we've discussed the basics of significance testing, and then we've done some things like one sample z-test, or was it t-test? Can't remember. We'll find out. Um, and then, yep, we've just done some simple tests related to significance testing. And then we've also looked at errors. Okay. And, whoa. This is the gist of Unit 10. Why is it doing that? Yep, okay. And then let's go back and work on this thing that I failed. Watch a video.
The mayor of a town saw an article that claimed the national unemployment rate is 8%. They wondered if this held true in their own town. So they took a sample of 200 residents to test. The null hypothesis is that the unemployment rate is the same as the national one, versus the alternative hypothesis, which is that the unemployment rate is not the same as the national, where P is the proportion of residents in the town that are unemployed. The sample included 22 residents who were unemployed, assuming that the conditions for inference have been met. And so that's the random, normal, and independence conditions that we've talked about in previous videos. Identify the correct test statistic for this significance test. So I like to rewrite everything just to make sure I've understood what's going on. We have a null hypothesis that the true proportion of unemployed people in our town, that's what this P represents, is the same as the national unemployment. And remember, a null hypothesis tends to be the no news here, nothing to report, so to speak. And we have our alternative hypothesis that no, the true unemployment in this town is different than 8%. And so what we would do is we would set some type of a significance level. We would assume that the mayor of the town sets it. Let's say he sets or she sets a significance level of 0.5. Versus the alternative hypothesis, which is that the unemployment rate is not the same as the national, where P is the proportion of residents in the town that are unemployed. The sample included 22 residents who were unemployed, assuming that the conditions for inference have been met. And so that's the random, normal, and independence conditions that we've talked about in previous videos. Identify the correct test statistic for this significance test. So I like to rewrite everything just to make sure I've understood what's going on. We have a null hypothesis that the true proportion of unemployed people in our town, that's what this P represents, is the same as the national unemployment. And remember, a null hypothesis tends to be the no news here, nothing to report, so to speak. And we have our alternative hypothesis that no, the true unemployment in this town is different than 8%. And so what we would do is we would set some type of a significance level. We would assume that the mayor of the town sets it. Let's say he sets or she sets a significance level of 0.5. And then what we want to do is conduct the experiment. So this is the entire population of the town. They take a sample of 200 people. So this is our sample. N is equal to 200. Since it met the independence condition, we'll assume that this is less than 10% of the population. And we calculate a sample statistic here. And it would be, since we care about the true population proportion, the sample statistic we would care about is the sample proportion. And we figure out that it is 22 out of the 200 people in the sample are unemployed. So this is 0.11. Now the next step is, assuming the null hypothesis is true, what is the probability of getting a result this far away or further from the assumed population proportion? And if that probability is lower than alpha, then we would reject the null hypothesis, which would suggest the alternative. But how do you figure out this probability? Well, one way to think about it is we could say how many standard deviations away from the true proportion, the assumed proportion, is it? And then we could say what's the probability of getting that many standard deviations or further from the true proportion? We could use a z-table to do that. And so what we want to do is figure out the number of standard deviations. And so that would be a z statistic. And so how do we figure it out? Well, we can figure out the difference between the sample proportion here and the assumed population proportion. So that would be 0.11 minus 0.08 divided by the standard deviation of the sampling distribution of the sample proportions. And we can figure that out. Remember, all that is, and sometimes we say, well, we don't know what the population proportion is, but here we're assuming a population proportion. So we're assuming it is 0.08, and then we'll multiply that times 1 minus 0.08. So we'll multiply that times 0.92. And this comes straight from, we've seen it in previous videos, the standard deviation of the sampling distribution of sample proportions. And then you divide that by n, which is 200 right over here. And we can get a calculator out to figure this out, but this will give us some value, which says how many standard deviations away from 0.08 is 0.11. And then we could use a z-table to figure out what's the probability of getting that far or further from the true proportion, and then that will give us our p-value, which we can compare to significance level. Sometimes you will see a formula that looks something like this. You say, hey, look, you have your sample proportion. You find the difference between that and the assumed proportion in the null hypothesis. That's what this little 0 says. Now, this is the assumed population proportion from the null hypothesis, and you divide that by the standard deviation, the assumed standard deviation of the sampling distribution of the sample proportions. So that would be our assumed population proportion times 1 minus our assumed population proportion divided by our sample size. And in future videos, we're going to go all the way and calculate this, and then look it up in a z-table and see what's the probability of getting that extreme or more extreme of a result and compare it to alpha.
P hat equals 0.14, and the test statistic was z equals some kind of fraction, some kind of square root. Then p hat goes first. I keep getting this wrong, but it's fine. 0.14, and the null hypothesis was 0.2, so minus 0.2. This is also a fraction. 0.2 times 0.8 over the sample size 100. Negative 1.5. Nice, okay. So one of these is that one. The sample proportion was 0.68. Okay, z equals minus 0.5 calculate the test statistic for Abdullah. Yep, okay. $400, 0.15 minus 0.2. Negative 2.5. Oh, it might be. It's a knot, so I wonder if it's double. Nope. Nice, okay. Let's just do the quiz again. It's this one. Type 1 error, wrongly reject. The batch is discarded when it actually doesn't contain the toxin. Which situation below would have the lowest probability of a type 1 error? Type 1 error is related to alpha 0.01. I think similar sample sizes. Which results in a test statistic of z equals 0.75. P-value for 0.75. Hmm. Point 0.7734. Fuck. Ah. Fuck. Point 0.0409. Fuck.
Let's review calculating confidence intervals for proportions. So let's say I have a population and I care about some proportion. Let's say I care about the proportion of folks that are left-handed. I don't know what that is, and so I take a sample of size n, and then from that sample, I can calculate a sample proportion. That's why I put that little hat on top of it. It's a sample proportion that's estimating our true proportion. Now I want to construct a confidence interval, but before I go down the path, I need to actually set up my conditions for inference, make sure that I meet them. And we've done this many times. So the first condition for inference is the random condition. I need to feel good that this is truly a random sample from the population. The
Random,
second one is often known
independent,
as the normal
normal.
condition. And that's the condition that, hey, in order to feel like the sampling distribution for the sample proportions is roughly normal,
Successes, failures, sample size. Oh no. So random is to do with experiment design, normal is to do with the expected failures and successes, and then independent is to do
n
with
times our sample proportion should be
10%
greater than or equal to
assumption.
10, and n times 1 minus our sample proportion should be greater than or equal to 10. We've seen that multiple times before. And then the third one is the independence condition. And there's two ways to meet this. Either the individual
For the difference between the two proportions, so this is likely going to be some sort of sampling distribution operation.
observations in our sample should be done with replacement. Or if it's not done with replacement, we can feel pretty confident about this if our sample size is no more than 10% of the size of the entire population. But let's say that we meet these conditions for inference. What do? Well, we set up a confidence level for our confidence interval that we're about to construct. And let's say we said it was a 95% confidence level. That would mean that 95% of the time that we went through this exercise, the confidence interval that we get would actually overlap with the true population proportion. And 95% is actually a fairly typical one. But from that confidence level, you can calculate a critical value. And the way that you do that, you just look up in a z-table. Once again, all of this is review. You would say, hey, how many standard deviations above and below the rate with the true? We said it was a 95%. Set up a confidence level for our confidence interval that we're about to construct. And let's say we said it was a 95% confidence level. That would mean that 95% of the time that we went through this exercise, the confidence interval that we get would actually overlap with the true population proportion. And 95% is actually a fairly typical one. But from that confidence level, you can calculate a critical value. And the way that you do that, you just look up in a z-table. Once again, all of this is review. You would say, hey, how many standard deviations above and below the mean of a normal distribution would you need to go in order to get, say, 95%, that confidence level of the distribution? And now we're ready to calculate the confidence interval. Confidence interval. It is going to be equal to our sample proportion plus or minus our critical value, times the standard deviation of the sampling distribution of the sample proportion. Now, there is a way to calculate this exactly if we knew what p is. If we knew what p is, this would be the square root of p times 1 minus p over n. But if we knew what p is, then we wouldn't even have to do this business of constructing confidence intervals. So instead, we estimate this. We say, look, an estimate of the standard deviation of the sampling distribution, often known as the standard error, an estimate of this is going to be the square root of, instead of the true population parameter, we could use the sample proportion. So p hat times 1 minus p hat, all of that over n. Now, the whole reason why I did this is covered in much more detail and much slower in other videos, is to see the parallels between this and a situation when we're constructing a two-sample confidence interval, or z-interval, for difference between proportions. What am I talking about? Well, let's say that you have two different populations. So this is the first population, and it has some true proportion of the folks that, let's say, are left-handed. And then there's another population. So let's call that P2. Maybe this is freshmen in your high school or college, and maybe this is sophomores. So two different populations. And you want to see if there's a difference between the proportion that are left-handed, say. And so what you could do, just like we've done here, is for each of these populations, you will take a sample. Here, we'll call that N1. And then from that sample, you calculate a sample proportion. Let's call that P1. And then from this second population, we do the same thing. This is N2. Notice, N1 and N2 do not have to be the same sample size. That's a common misconception when doing these things. These could be different sample sizes. And then from that sample, you calculate the sample proportion. Now, after you do that, you would want to check your conditions for inference. And it turns out that the conditions for inference would be exactly the same. Do both of these
Huh? Oh,
hat 1 over N1
forgot to
plus
unpause.
P hat 2 times 1 minus P hat 2 over N2. And then you put that there, you have constructed your confidence interval. And once again, how would you interpret that? Well, let's say your confidence level is 90%. And from that, you're able to construct this confidence interval. That would mean that 90% of the time that you go through this exercise, your confidence interval would overlap with the true difference between these population parameters, the true difference between these population proportions. Now, where did this thing come from? Well, you might notice some similarities here. This part over here is an estimate, or it's approximately equal to the variance of the sampling distribution of the sample proportion for our first population. And then this right over here, once again, is approximately going to be equal to the variance of the sampling distribution for the sample proportions for this population, for P2. How did I know that? Well, look, if this is approximately the standard deviation, you square that, you approximately get the variance. And so the big takeaway is that the variance for the sampling distribution of the difference is just the sum of the variances of each of those sampling distributions. That's a lot of big mouthful, I know it can get confusing, but of the difference is just the sum of the variances of each of those sampling distributions. That's a lot of big mouthful, I know it can get confusing, but hopefully that the difference is just the sum of the variances of each of those sampling distributions. That's a lot of big mouthful, I know it can get confusing, but hopefully that makes sense. And that's where this formula comes from. And so it's really not that much more to remember. In the next few videos, we're going to do many more examples, both looking at these conditions and calculating confidence intervals and critical values.
Okay, so confidence levels for the Z, yeah, Z star. Confidence intervals. Need to do this again because I don't quite understand.
Let's review calculating confidence intervals for proportions. So let's say I have a population and I care about some proportion. Let's say I care about the proportion of
Let's
folks
go
that
to the
are...
next video.
A sociologist suspects that men are more likely to have received a ticket for speeding than women are. The sociologist wants to sample people and create a two-sample Z interval. In other videos, we introduce what that idea is, to estimate the difference between the proportion of men who have received a speeding ticket and the proportion of women who have received a speeding ticket. Which of the following are conditions for this type of interval? Choose all answers that apply. So like always, pause this video and see if you can answer it on your own.
Okay.
Alrighty, let's review our sample, but now we need to sample the following are conditions for this type of interval. So that's right, that's trees in a forest. They are curious if there's a difference in the proportion of trees that are infected in the north and south sections of the forest. They want to take a sample of trees from each section and do a two sample z-test to test their hypothesis. Number, both region of the forest. This is the interval or confidence interval that the both samples have these, and at least 10 sample equal number of trees from each region of the forest. This is a very common misconception that when you're doing a two-sample z, but that is actually not the case. So we can rule that one out. Condition that we just looked at. So this would be our only choice, and we're
Okay, let's see.
Duncan is investigating if residents of a city support the construction of a new high school. He's curious about the difference of opinion between residents in the north and south parts of the city. He obtained separate random samples of voters from each region. Here are the results. So let's see, in the north, 54 out of the 120 said they want the school, 66 said they didn't. In the south, 77 said they wanted the school, 63 said they didn't. Duncan wants to use these results to construct a 90% confidence interval to estimate the difference in the proportion of residents in these regions who support the construction project, P sub S minus P sub N. So these are the true parameters for the difference between these two populations. Assume that all of the conditions for inference have been met. All right, which of the following is a correct 90% confidence interval based on Duncan's samples? So pause this video and see if you can figure that out, and you will need a calculator, and depending on your calculator, you might need a z-table as well. In a previous video, we introduced the idea of a two-sample z-interval. We talk about the conditions for inference. Lucky for us here, they say the conditions for inference have been met. So we can go straight to calculating the confidence interval. And that confidence interval is going to be the difference between the sample proportions, so P sub S hat, so the sample proportion in the south, minus the sample proportion in the north. It's going to be that difference, plus or minus our critical value, z star, times our estimate of the standard deviation of the sampling distribution of the difference between the sample proportions. And that is going to be, our estimate is going to be p hat sub s times 1 proportions. And that is going to be, our estimate is going to be p hat sub s times 1 minus p hat sub s, all of that over the sample size in the south, plus p hat sub n times 1 minus p hat sub n, all of that over the sample size in the north. Okay, so our sample proportion in the south, I'll later use a calculator to get a decimal value, but this is going to be, in the south, we have 77 out of 140 supported, so this is going to be 77 out of 140. In the north, this...
Okay, so the confidence interval for the difference between the two samples is p hat sub s minus p hat sub n plus minus. Okay, that's the lower and upper bound. This is your critical value, which is given. Okay. No, actually, plus minus standard error. Pretty sure that's standard error. Yep, okay. Normally this would be p hat times 1 minus p hat over n. Now we're combining them. Okay.
is going to be 54 out of 120. 54 out of 120. What is my critical z value? Well, here I'm going to have to either use a calculator or a z-table. Remember, we have a 90% confidence interval. And so
5% on both sides.
Here, if this is a normal distribution, and you want to have a 90% confidence interval, that means you're containing 90% of the distribution, which means each of these tails, well, combined they would have 10%, but each of them would have 5% of the distribution. And so I'm going to look at a z-table that figures out how many standard deviations below the mean do I need to be in order to
5%.
get 5% right over here. And then that's going to tell me, well, if I'm that far below or above, that's going to be my critical z value. So let me get that z table out. So I care about 5%, and I'm using this in a bit of a reverse direction. But let's see, 5%. So this is a little over 5%, getting closer to 5%, even closer to 5%, and now we've gotten right below 5%. So we're going to be in between this and this. I could just split the difference, and I could just say 1.6, let's just say 1.645 to go right in between. So this is going to be approximately equal to 1.645. And then, let's see, we know what p hat sub s is. We know what p hat sub n is. In the south, our sample size is 140. And in the north, our sample size is 120. And so now I just have to type all of this into the calculator, which is going to get a little hairy, but we will do it together. For the sake of time, we'll accelerate this typing into the calculator. But I'm going to start with calculating the upper bound, and then we'll calculate the lower bound. And then I think I've closed all my parentheses, and so I think we're ready to get the upper bound is going to be equal to 0.218, or approximately 0.202. So we can immediately look at our choices and see where's at the upper bound. And so this one is looking pretty good, 0.202. But let's get the lower bound now. So I got my calculator back. Instead of right, 0.00 choice.
Okay, let's
Duncan is
look
investigating
at
if
the
residents of a city support the
formula one more
202.
time.
So we can immediately look at our choices and see where's at the upper bound. And so this one is
Okay, so p hat differences plus minus. This is the lower and upper bound. Z star, or the critical z value, which is based on the confidence level. You get that by looking at the z value that corresponds to the area under the normal curve, which for a single bound gives you the correct probability. And then you multiply this to standard error for both. And standard error, standard deviation for both sampling distributions. Okay. Sample results. Samples. Yep. Okay. Let's see if we can remember that. Okay, bounds. Bounds. Lower bound, upper bound. Okay, so it's one of these. 95% confidence. It's 2.5% on each side. So 0.025. I am lost. 0.025. Okay. Negative 1.96. Is that right? Yeah, that's right. Okay, 1.96. And then differences here are in sample 1, 0.8 and 0.2. Eighty over 100, 60 over 100. It's this one. Based on these samples, okay, we gotta do some calculations. Yes, yes. Okay, so 0.2 minus 0.25 plus minus z star 0.05 on both sides. Point 0.005. 995. Point 2.55. Just calculate the upper bound. This needs to be multiplied to square root, something like this. And do the bottom first. Because it's standard deviation, I'm pretty sure we're supposed to add that. Let's just double check the formula. Difference. Oh no, so it's supposed to be like this. Okay, let's do it again. Oops. Zero point 0.018. Hmm. Fuck it, we'll go with this one. Okay. Oh, fuck. I got the sample sizes mixed around. And form is wrong. I guess I inputted something incorrectly. Okay, break. Okay, let's do this again. This is following the correct 95% confidence interval based on their data. Okay, we need a z-score. Nope. Okay. Something like this. Uh, equals. So we're looking at one of these. Z star equals 95%, so 2.5% on each side. 0.025. Negative 1.96. 1.96 times, times square root of this. Okay. 600, 400, and then this one is 5, 3, 0.725, something like this. Calculator. Times 1.96, 0.057. Okay, Must be C. It's one of these ones. I remember the critical C value a while ago. Okay. It is D. D. Yeah, it's plus, not minus. Bonus question. Solve this again. Okay. P hat. Let me write down the formula first. So it's P. That's good practice. P hat north minus P hat south. This is the formula for constructing a confidence interval based on the difference of two samples. Okay. Z star times square root I'm lazy. Okay. I need to do it anyways. 0.45. 55%. 5% on both sides. 0. Negative 1.65. 1.645. One 20, 140. Start with the right hand side because it's complicated. No, it's not right. Let's see.
We're now going to explore hypothesis testing when we're thinking about the difference between proportions of two different populations. So here it says, here are the results from a recent poll that involved sampling voters from each of two neighboring districts, District A and District B, and folks were asked whether they support a new law or not. And from each district, we took a sample of 100 voters, and then we were able to calculate the proportion from that sample that supported the law. And then here we have the combined data, including the combined proportion. And we're asked, does this suggest a significant difference between the two districts? And so this is asking for a hypothesis test. And the way we would do that is we would set up our null hypothesis.
Okay, let's have a look.
We're now going to explore hypothesis testing when we're thinking about the difference between proportions of two different populations. So here it says, here are the results from a recent poll that involved sampling voters from each of two neighboring districts, District A and District B, and folks were asked whether they support a new law or not. And from each district, we took a sample of 100 voters, and then we were able to calculate the proportion from that sample that supported the law. And then here we have the combined data, including the combined proportion. And we're asked, does this suggest a significant difference between the two districts? And so this is asking for a hypothesis test. And the way we would do that is we would set up our null hypothesis. Remember, our null hypothesis is the one that we would assume that there is no difference. So we would assume that the true proportion of folks in District A that support the new law is equal to the proportion in District B that support the law. Or another way to think about it is that the difference would be equal to 0. And our alternative hypothesis is that the absolute difference between the proportions is not equal to 0. And if we were doing an all-out hypothesis test, we would set a significance level, which we usually denote with an alpha. Oftentimes, it might be a 10% significance level or a 5% significance level. Let's say we set it at a 5% significance level. And what we would do is we would say, all right, let's assume that the null hypothesis is true. And assuming the null hypothesis is true, what is the probability of getting a difference between our sample proportions this extreme or more? And if that probability is less than our significance level, then we reject the null hypothesis, which would suggest the alternative. Now, before we go deeper into our inference, we want to test our conditions for inference. And we've seen these many times before. You have the random condition, where you would need to feel good that both of these samples are truly random. Failure sampling with replacement, or there's at least 1,000 folks in District A and at least 1,000 folks in District B, and that would allow us to meet the independence condition. And so with that out of the way, let's assume the null hypothesis. And let's just start thinking about the sampling distribution of the difference between the sample proportions, assuming that null hypothesis. So the first thing I want to think about is, what is going to be the standard deviation of the difference in the sampling distributions? Well, we have seen in a previous video when we talked about differences of proportions, we could think about the variance. So the variance of the sampling distribution. And there's a lot of notation here. So the variance, this is going to be equal to the variance of the sampling distribution of the sample proportion from District A plus the variance of the sampling distribution of the sample proportion from District
standard
B.
deviation is just
Now, in general, you can
variance,
figure out the
so
variance of the sampling distribution of a sample proportion with the following formula. We've seen this before. The variance of the sampling distribution of the sample proportion is going to be equal to our true proportion times 1 minus our true proportion, all of that over your sample size. Now, in either situation, we don't know the true proportions for District A or District B. That's why we are in this, that's why we're even doing this hypothesis test to begin with. But we can try to estimate it. Remember, we're assuming that the true proportions are equal, even though we might not know what they are. And what is going to be our best estimate of that true proportion if we assume that District A and District B have no difference in terms of the number of people who support the new law? Well, the best estimate would actually be the combined sample proportion right over here. And so to estimate these values, we use this combined sample proportion in the place of P over here. So we could say that this is going to be our combined sample proportion times 1 minus our combined sample proportion. All of that over our sample size. And since we're assuming that there's no difference between District A and District B, this would also apply to that right over there. So let me rewrite this again. The standard deviation of the sampling distribution of the difference of the sample proportions from District A and District B is going to be roughly, remember, we weren't able to calculate it exactly, but we're using this combined proportion as our best estimate. Let me do a big square root right over here, big radical. And so underneath that, we're going to have our estimate of this, which is 0.55 times 1 minus 0.55, so 0.45 over 100, plus our estimate of this, which is 0.55. It's the same thing again, times 0.45. And remember, that's because we're assuming the null hypothesis is true. All of that over this sample size, all of that over 100. And now we can get our calculator out to actually calculate it. And so we get divided by 2 to 0.0. We scored that extreme or more. And so our z at proportions. So all of that over 0.06 over 0, the sub p hat sub a minus p hat sub b. All of that over our estimate of the standard deviation.
is there a difference? Okay.
Of the sampling distribution of this difference between the sample proportions. So all of that over 0.07. Now this up here in yellow, it's 0.58 minus 0.52. This is going to be equal to 0.06 over 0.07. 0.07, we can get our calculator out for this again. And so we have 0.06 divided by 0.07 is going to be, it's approximately 0.86. So this is approximately 0.86. Now what's the probability of getting something this extreme or more extreme? Let me just make sure we can visualize it properly. So if this is our sampling distribution of the difference between our sample proportions, and we're assuming the null hypothesis, so the mean of our sampling distribution is going to be zero right there. We just got a result that is less than a standard deviation above the mean. So we just got a result. So if this is one standard deviation, two standard deviations above the mean, one standard deviation below the mean, two standard deviations below the mean, we just got a result that puts us right there. And if we asked ourselves, what's the probability of getting a result at least that extreme, we would say, okay, it would be, what's the probability of getting a result all of this area right over here? And it would also be, what's this area on the other side of the mean? And we know that this is over 30%, because even if you just exclude one standard deviation above and below the mean, if you say anything more extreme than that, so if you put this area and this area, you're looking at roughly 31 or 32%. So the probability of getting something at least this extreme is going to be over 30%. And so it's definitely going to be higher than our significance level. It's actually completely reasonable to get a difference.
Yeah, you could have just pulled up a z table to show
this extreme if we assume the null hypothesis is true. In future videos, we can go even deeper, where we can actually just look this up on a z-table to calculate these areas more precisely, and we can compare them to the significance level. But here, it's not even close.
Okay, so this video is pretty simple. Nothing really new here. So calculated the standard deviation of the difference of these two samples, and then he calculated z-score, which is b hat 1 minus b hat 2 over 0.07, which is standard deviation.
Derek is a political pollster tracking the approval rating of the prime minister in his country. At the end of each month, he obtains data from a random sample of adults on whether or not they currently approve of the prime minister's performance, using a separate sample each month. Derek wants to test if the proportion of adults who approved was significantly lower in December than it was in November. Which of the following is an appropriate set of hypotheses for Derek's significance test? Pause this video and see if you can figure it out on your own.
Okay. Significantly lower in December. Probably be A, right? Null hypothesis is the hypothesis of no difference, so it's equal. Wants to test if the significantly lower in December.
All right, so let's think about ways to write a null hypothesis. That exactly, if the proportion he's wanting to see proportion sees a legitimate null hypothesis for what we're trying to do, so we could rule out D. And then the other one is this: Derek wants to test if the proportion here with December is significantly lower and significantly different. They have the same example, showing heads when they are flipped. She flips each coin 100 times to test if there is a significant difference in the proportion of flips that they each land showing heads.
It'd be D, probably.
Which of the following is an
significant difference?
The proportion of heads with a dime is significant.
Okay, exercise. Design A is larger, okay. Oh. I just noticed that. Yeah, okay. Design A. Iron 2017. If the proportion of adults who approved was significantly lower in December. Lower in December. Lower. Hopefully we can finish this unit today. Be pretty good. This
We
unit
are
is
told that
packed with
researchers
stuff.
suspect that myopia, or nearsightedness, is becoming more common over time. A study from the year 2000 showed 132 cases of myopia in 400 randomly selected people. A separate study from 2015 showed 228 cases in 600 randomly selected people. So what we're going to do in this video is do a hypothesis test to see if we have evidence to suggest the researcher's suspicion that myopia is becoming more common over time. If at any point you are inspired, I encourage you to pause the video and try to work through things on your own, but here I go. I'm going to do it with you. So let's just start off by setting our null and alternative hypothesis. So remember, our null hypothesis, this would be that the no news here. So that would be that, contrary to their suspicions, that myopia is not becoming more common over time. And so the way that we're measuring more common over time is we could look at the proportion of folks who have myopia in 2015 and compare that to the proportion in 2000.
Yep,
so our null
two
hypothesis is that
samples.
there's no difference, is that the true proportion of folks who have myopia in 2015 is equal to the proportion of folks who have myopia in 2000. And then our alternative hypothesis, remember, they suspect that it's becoming more common over time. So that would be a situation in this go inference. And we've done this many times before. You have your random condition, and it looks like we meet that because in both of the samples, we have 400 randomly selected people, so that looks good. Then you have your normal condition. And to meet your normal condition, your number of successes and failures, those mentioned that we sample meeting author of 2015 and 2000, and our significant. So the sample distribution of the difference between the sample proportions in 2015 and 2000. Now, this is going to be, and I will say approximately equal to, we can calculate this numerator exactly, but this denominator we are going to estimate. So this numerator case, we use the conversion type proportion, 132, the expression when we're trying to estimate our standard deviation of this sampling distribution. So this is going to be side 200 between the proportions in 2015 and 2000. And so to get a better estimate of the true proportion, well, we should just add up our samples. So our sample size would be 600 plus 400 plus 132. We could write that as p hat sub c. And the reason why we use the combined proportion, we've talked about this in previous videos, is remember, when we do our hypothesis test, we assume that our null hypothesis is true. And if our null hypothesis is true, there's no difference between the proportions in 2015 and 2000. And so to get a better estimate of the true proportion, well, we should just add up our samples. So our sample size would be 600 plus 400, 600 plus 400. And the number of cases of myopia would be 228 plus 132. Plus 132, which would get us to, what is this, 360 over 1,000, which is equal to 0.36. And we can use that inside the expression when we're trying to estimate our standard deviation of this sampling distribution. So this is going to be 0.36 times 1 minus 0.36, which would be 0.64, over the sample size in 2015, which is 600, plus 0.36 times 0.64 over the sample size in 2000, which is equal to 400. And let's see, before I even get my calculator out, I think I can simplify this a little bit. (228 over 600). 228 divided by 6 is going to be equal to 38. So this would be 0.38. Let's see, 132 divided by 4 would be 33. So this would be 0.33. And so our entire numerator is going to be 0.05. So 0.05. And so now I could put this into my calculator, and I will get 0.05 divided by the square root of, let's see, I'm going to have 0.36 times 0.6.4. So this is going to be approximately 1.61. And so one way to think about it is the difference that we got between our sample proportions between 2015 and 2000 of 0.05, that is 1.61 standard deviations above our mean of our sampling distribution if we assume that the null hypothesis is true. And so from this we can calculate our p-value. Remember, our p-value is equal to the probability that our z-score is at least that big, is greater than or equal to 1.61. And one way to think about it, if we look at the sampling distribution, or really we could just look at any normal distribution now since we've normalized for z. So we're looking at 1.61 standard deviations above the mean. So z is equal to 1.61. So we're thinking about this area right over here. That would be our p-value. And to help us with that, we can get out a z-table. And we see this z-table gives us the cumulative area up to some z-score. And so we would just have to, whatever this gives us, we would just have to do 1 minus that. So if we go to 1 that, we can get out a...
But basically, all we're doing here is, instead of, I think we were doing standard deviation last time. What was the last video we did? Hypothesis for two proportions. Difference in proportions. Oh, I see. Okay.
We go to 1. Since we have normalized.
We use a different formula to get a z-value, and we compare it to the p-value, and then we get the p-value from the z-value, and then we compare that to the alpha. Okay.
For z. So we're looking at 1.61 standard deviations above the mean. So z is equal to 1.61. So we're thinking about this area right over here. That would be our p-value. And to help us with that, we can get out a z-table. And we see this z-table gives us the cumulative area up to some z-score. And so we would just have to, whatever this gives us, we would just have to do 1 minus that. So if we go to 1.61, we get 0.9463. So it would be 1 minus 0.9463 is equal to 1 minus 0.9463, which is equal to, let's see, it's 0.0537, 0.0537. And notice, this p-value is ever so slightly higher than our significance level. But this is why we want to set our significance level ahead of time. We don't want to get tempted to say, oh, I'm so close, let me just raise my significance level a little bit more so that I can reject my null hypothesis, and then I can have something that I can tell my friends about. No, that would not be good science. That would not be good statistics. We have to be disciplined. So here, because our p-value is greater than our significance level, even though it's by a very small amount, we fail to reject our null hypothesis. And another way to think about it in terms of the context of the question.
Okay. Formulated our hypothesis. We have our conditions for what?
In this scenario, myopia would be becoming more times, and we see that that is the case. Normal case, affected or not, which would suggest our alternative. You have to look at your conditions for inference, and we've done this many
Conditions for inference. That is what it's called. Okay.
Significance level of the difference. Now, this estimate sign is we use the combined proportion, and we could write that as p hat sub c. And the reason why we use the combined proportion, we talked about this in difference between the proportion.
Okay, we set a significance level. Okay. There's a difference of p hat.
Proportions in 2015 and 2000. And so to get a better estimate of the true proportion, well, we should just add up our samples. So our sample size would be 600 plus 400, 600 plus 400. And the number of cases of myopia would be 228 plus 132. Let's add up our samples when it's p hat sub c. And the reason why we use the combined proportion, we've talked about this in previous videos, is remember, when we do our hypothesis test, we assume that our null hypothesis is true. And if our null hypothesis is true, there's no difference between the proportions in 2015 and 2000. And so to get a better estimate of the true proportion, well, we should just add up our samples. So our sample size would be 600 plus 400, 600 plus 400. And the number of cases of myopia would be 228 plus 132. Plus 132, which would get us to, what is this, 360 over 1,000, which is equal to 0.36. And we can use that inside the expression when we're trying to estimate our standard deviation of this sampling distribution. So this is going to be 0.36 times 1 minus 0.
Estimating the standard distribution of the sampling distribution.
0.36, which would be 0.64, over the sample size in 2015, which is 600, plus 0.36 times 0.64 over the sample size in 2000, which 400. Is equal to 400.
Yep.
And let's see, before I even get my calculator out, I think I can simplify this a little bit. 228 over 600, 228 divided by 132, 0.05 divided by the square root of 4 is going to get me approximately 1.61. So
that's a z-score.
61.
And their alternative hypothesis was 2015 is greater than 2000.
Get out to 1 point our significance level ahead of time. We don't want to get.
Yep. Let's try this out. Okay, 50 throws. Null. Alternative. Uh, let's do old. Oh, well, it's not even asking for anything related here. It's just asking for the Z statistic. Okay, that's fine. Why is your minus 0? Okay. 0.6 versus 7.6.76. Well, remove that. Remove that. Let's see how they are different. Okay, so sample size. Oop, different sample size. This is a different sample size and a different um different numerator. Okay. The top should be the same. And it's 50 plus 50, so it's no, it's supposed to be 50 below each. I think it should be form A first. Yep, that's what I was thinking. Oop. what we're doing makes sense because what we know from calculating p-value is the probability that you get your sample statistic given that your null hypothesis is true, and the reason why we're trying to reject that when we do significance testing is because, well, the intuition behind it is that if the probability that you get your result, your test result, given that your null hypothesis is true, is so low, then you should just, it makes more sense to assume that it is not true. And in this case, we are doing that same thing where assuming that the null hypothesis is true. So we're living in this world where it's true. Um, Given that it's true, do the following calculations, and this denominator reflects that. Okay. 70, 30, 100, or 2000. That is 0.05. Okay, so not that, not that. Alternative hypothesis is, okay, Alaska, Minnesota. Hmm. Goes Alaska first. And it's 1,000 each. That should be D. Yeah, yeah, yeah. P-value in a two-sample z-test for the difference of proportions. Okay. P-value associated with these sample results. Okay. Z equals this minus 0, something like this. Oops. Plus N over here is 80. Oh wait, women first. Okay. 100, 80, minus 0.3. Oh yes, and then the standard deviation would be, since we're assuming that the null hypothesis is true, we add 70 over 180. We can just say 0.389. Damn. What? I wonder what someone hit. Someone definitely hit something, right? I wanted to see like flash and okay. You okay? No worries. How is the? You still hot?
No, it was just to get rid of air flow.
I'm back. Second deviation. Well, let's just use 0.39 for simplicity. Okay. Oh no. 39. And 0.61. And it is a two-tailed test. .46. Check negative 2.46. .0069. Minus 2. .0138. .0138. Nice. Okay, another one. Z equals Minnesota, Wisconsin, Random sample, Minnesota, Wisconsin. Yeah. Yeah. 1.15. 0.1251. Oh, wait, what kind of test is this? Greater than. Okay. Point 0.8749. 0.1251. I keep doing this with the formula just so I can really nail it into my head. 0.49. I think this is wrong, but let's see. Huh, no, I was right. Let's try to do this one without a calculator. Okay, let's do the denominator first, okay. 160 plus 180 divided by 400. Okay, this times that divided by that times 2. Square root that. Denominator done. Okay. Alternative hypothesis greater than. Okay, US then Mexico. So 0.2 p hat 1 p hat US p hat Mexico 0.2 minus 0.1 denominator 2.8 greater than 2.8 0.9974 1 minus that 0.0026 it's less than 0.01. Nice. Yeah. That's pretty good.
A veterinarian is studying a certain disease that seems to be affecting male cats more than female cats. They obtain a random sample of records from 500 cats. They find 24 of the 259 male cats have the disease, while 14 of 241 female cats have the disease. The veterinarian uses these results to test their null hypothesis that the true proportion is the same amongst the male and female cats versus the alternative hypothesis that the proportion of males who get the disease is actually higher than the proportion of females. The test statistic was z is equal to 1.46, and the p-value was approximately 0.07. That's useful. They've done a lot of work for us. Assume that all conditions for inference were met. At the alpha equals 0.10 level of significance, is there sufficient evidence to conclude that a larger proportion of male cats have the disease? So pause this video and see if you can answer that.
Comparing p-value to significance level for test involving difference of proportions, okay? Random sample of 500 cats. Okay, so they're from the same sample. No, well, no, they're not. I mean, they are, but okay. Test statistic z equals 1.46. P-value 0.07. All conditions for inference are met. Alpha 0.1 level of significance. Sufficient evidence to conclude that a larger proportion of male cats have the disease. Wait, this is a 2-minute video. Yeah, fuck yeah. What am I doing?
All right, so and what is that? Jack is indeed of that, which is, and I'll, so
Why
the
is
choice
this
that you would
even a
pick might be
video?
something like, because our p-value is less. A university offers a certain course that students can take in person or in an online setting. Teachers of the course were curious if there was a difference in the passing rate between the two settings. Data from a recent semester show that 80% of students pass the in-person setting and 75% of students pass the online setting. They were willing to treat these as representative samples of all students who may take each setting of the course. The teachers use those results to make a 95% confidence interval to estimate the difference between the proportion of students who pass in each setting of the course. So this is a 95% confidence interval for the difference between the proportion who pass the in-person course and the online course. The resulting interval was approximately, went from negative 0.04 to 0.14. And just to make sure we understand what this is saying 95% of the time that you go through this, because we're talking about a 95% confidence interval, 95% of the time you take these samples and then you construct a confidence interval for the difference in proportions, that it will actually contain the true proportion. They want to use this interval to test their null hypothesis that the true proportions are the same versus their alternative hypothesis that their true proportions are different. Assume that all conditions for inference have been met. Based on the interval, what do we know about the corresponding p-value and conclusion to their test? So pause this video and try to figure it out on your own. All right, so what's interesting here is we're going to
So I think that with this confidence interval, it's quite interesting because this is the proportion of students who pass. So obviously you can't really have a negative proportion. So it means that on the high end, 0.14, it's like 14% of students are passing. So I don't know.
use a confidence interval to think about a hypothesis test. And remember, in a hypothesis test, we assume that our null hypothesis is true. We'll assume this, and there's another way we could write it. We could write it like this, that the difference between the in-person
It's the same.
hypothesis level, and so let's say we set the ability of the results of getting the results to be unlike confidence interval. And it turns out that if the sum of your confidence level and your significance level is equal to 100%, and you're doing a two-sided hypothesis test. So you're thinking about, well, our alternative hypothesis isn't just that the in-person is greater than the online or that it's less than the online, it's that they are different. So we have a two-sided hypothesis test. In these situations, you can actually make some inferences about your p-value from your confidence interval. Think about it this way. We are assuming our null hypothesis is true when we do this hypothesis test. And so when we construct a 95% confidence interval, we would expect that 95% of confidence intervals
Contains the
intervals
true parameter.
would overlap with 0. Where did I get 0 from?
What?
Remember, this is a confidence interval for the difference in proportions. And our null hypothesis is that the true difference in proportions is 0.
Oh.
So 95% of the time that we do this, if we assume that the null hypothesis is true, we will overlap with 0. Or another way you could think about it, 5% of confidence intervals
Do
would
not overlap.
not overlap with 0. And so if you are in a situation where you go through this process, you try to construct a 95% confidence interval, and you don't overlap with your assumed difference of the true proportions from your null hypothesis, well, in this situation, your p-value is going to be less than your 5% significance level. So in this situation, you would reject your null hypothesis. And in this first situation, your p-value is going to be greater than, or hypothesis test, we will assume that this is true. And then in a traditional hypothesis test, we set some significance level. And so let's say we set that significance level at 5%, and that is a very typical significance level. And if the results we get, if the probability of the results of getting the results that we do get for the sample, the difference in the sample proportions is less than 5%, we say, hey, that's pretty unlikely. We're going to reject the null hypothesis, which will suggest the alternative. But here we have something interesting. We have a confidence interval. And it turns out that if the sum of your confidence level and your significance level is equal to 100%, and you're doing a two-sided hypothesis test. So you're thinking about, well, our alternative hypothesis isn't just that the in-person is greater than the online or that it's less than the online. It's
Yes.
that they are different. So we have a two-sided hypothesis test.
Yep.
In these situations, you can actually make some inferences about your p-value from your confidence interval. Think about it this way. We are assuming our null hypothesis is true when we do this hypothesis test. And so when we construct a 95% confidence interval, we would expect that 95% of confidence intervals would overlap with 0. Where did I get 0 from? Remember, this is a confidence interval for the difference in proportions. And our null hypothesis is that the true difference in proportions is 0. So 95% of the time that we do this, if we assume that the null hypothesis is true, we will overlap with 0. Or another way you can think about it, 5% of confidence intervals would not overlap with 0. And so some inferences about your p-value from your confidence interval. Think about it this way. We are assuming our null hypothesis is true when we do this hypothesis test. And so when we construct a 95% confidence interval, we would expect that ninety-five percent of confidence intervals would overlap with 0. Where did I get 0 from? Remember, this is a confidence interval for the difference in proportions. And our null hypothesis is that the true difference in proportions is 0. So 95% of the time that we do this, if we assume that the null hypothesis is true, we will overlap with 0. Or another way you could think about it, 5% of confidence intervals would not overlap with 0. And so if you are in a situation where you go through this process, you try to construct a 95% confidence interval, and you don't overlap with your assumed difference of the true proportions from your null hypothesis with 0. And so if you are in a situation where you go through this process, you try to construct a 95% confidence interval, and you don't overlap with your assumed difference of the true proportions from your null hypothesis, well, in this situation, your p-value is going to be less than your 5% significance level. So in this situation, you would reject your null hypothesis. And in this first situation, your p-value is going to be greater than or equal to your alpha level, and you would fail to reject. So what's the situation here? Well, our interval actually does include the assumed difference in true proportions from the null hypothesis. So that means, assuming the null hypothesis, we are in this first scenario. This is one of the 95% of confidence intervals where we actually did overlap with the true parameter that we are trying to estimate. And so in that situation, our p-value is going to be greater than or equal to our alpha, which in this case is 5%. And so we fail to reject the null hypothesis. And so there isn't evidence to suggest that there is a true difference in passing rates between the in-person and the online exam.
Let me try parrot what he said. Oops.
And so there.
Okay. So they've given us a confidence interval. They've told us what it was. They've given us null alternative hypothesis. Yep. And then we have a significance level, 5%. And from here, okay, let's do the exercise. Hmm, 0.05 plus 0.07. Mm. Show me in a bit. I have 10 minutes left on my math video. So basically it's saying if it contains 0, reject. Otherwise, fail to reject. Okay. No. Plus minus. It doesn't contain 0, so we fail to reject. No, it doesn't contain 0, so we reject. But it's a 0.1. Does it make a difference? No, it doesn't. Yes. 0.46, alpha 0.1, no. P-value is greater than 0.1. Okay, yeah. Question, quiz. We'll finish up with this quiz and then leave the unit test for next time. Okay. Uh, Oh, 0.05 on each side. Negative 1.65. Ah, it's wrong again. Point 0.005. Negative 2.57. 2.57. No, wrong again. Oh my god, finally. Okay, I will end the video here, and I will quickly review what we've done together in this video so far. It's looking pretty good. Okay, so we worked on conditions for inference. Yep. Oh wait, hold on, unit 10. We worked on the confidence for inference on two proportions. We did two sample z interval for the difference of proportions. Hypothesis for testing for the difference of proportions. Yep. Test statistic in two sample z test for, again, difference of proportions. So difference of proportions was the main thing we've worked on. So you're getting the difference of two sample proportions, and we are doing several things such as seeing if our confidence intervals are valid. We're generating confidence intervals for that new sampling distribution, which is the difference of the two sample results. We did a bunch of hypothesis stuff, which is pretty simple. Don't need to go into in depth with that. I'd say the main thing we've worked on is two sample z-test and interpreting test results. And some things as well, like interpreting the p-values based on already existing confidence intervals and relating it back to the null hypothesis and p-value. If you like the video, subscribe. Okay, see ya.